Okay, then let's get started. So from the last week, we are discussing some kind of the ideas in terms of like how we can apply some kind of the pre-trained diffusion and flow models for some kind of the really broader the applications, especially in terms of like injecting some kind of the guidance in the generation the period. So those are some kind of some techniques that we discussed the last time. And for the discussion of the inference time guided generation, like one thing that I briefly mentioned was about basically this technique that I call the diffusion desynchronization, which was basically the case that we are making some kind of the data in the other forms, like some 3D things or some kind of panoramic images and the many other things, like those things and the panoramic images. We also have seen those kind of the many examples for the synchronization in terms of that. These are basically all the examples that we are making some kind of the data in the form that we didn't have the data in the training of the diffusion model, right? So those are all the cases that we are basically making some kind of the data, not the form that has been used for the training of the diffusion models, but the data that can be actually mapped to the data that we have seen during the training. In a way that we are basically performing the denoising the process from the multiple perspectives, like the simultaneously, in a way that these are basically integrated in the canonical space that we defined last time. So this was kind of the interesting idea in terms of that if you have some kind of any pre-trained model, then this kind of the pre-trained model can be used not only to generate the data that we have seen during the training time, but also for the other data that can be mapped to the data that we have seen during the training. So this is also kind of the one specific kind of example in terms of widening this kind of the range of the applications of the pre-trained and the diffusion and the flow models. And speaking to this direction, we are also going to briefly discuss some kind of some very practical and the simple idea, which is called the score distillation desampling. And this idea also can be applied to the many other cases as well. So here the basic kind of thing is that as we also discussed from the beginning of like this class, the diffusion models can be applied not only to generate the images and the videos, but into to generate some kind of the many the diverse type of the data, like the audio or the molecular structure, for the weather forecasting, for the many other things. But here the basic question is that how much data do we need to produce some kind of the realistic data? Actually, this is really very practical question that I also received multiple times when I was basically discussed like making some kind of models for the people, especially in the industry. They easily very ask like, so how much data do we need to make some kind of the good the diffusion model or some kind of the other diffusion model? And obviously there's no clear answer, right? Can you see, like, so you also trained your own diffusion flow model, right? Also for the image degeneration challenge. Did you feel that the amount of the data was like sufficient to make some kind of the good quality of the images? Did you get any sense of like how many images that you need to train some diffusion model for some specific type of data? I mean, if you really try to apply those kind of the ideas for the generative models to produce like many other types of data, then this is really some practical problem that you will face. Like, let's say like you want to make some kind of the diffusion model for some kind of the medical imaging, some kind of the images like that are having some kind of indication of some kind of the disease, for example, for some kind of to train some other the AI models for some diagnosis for something, then how much data do you need? So this is really kind of the non-trivial the question in terms of like how much kind of the amount of the data will basically guarantee the quality of the outputs. So I'm not gonna say any kind of answer for that, but obviously more is better, right? In all the cases, if we have some kind of the more amount of the data, that would be much better in terms of improving the quality of the outputs. The problem is that for many cases, for many applications, we will not have some kind of that kind of the big scale of the data. For the images, the reason why we are seeing some kind of the really good quality of the outputs would be not only because of some kind of the advances of the generative models that we are seeing, but also because of the scale of the data, right? For the images, we have seen that there are like billions of the images. For the videos, we also might have some kind of some other the billions of the data. But how about the other things? For the audio or some kind of molecular structure or some motions here, for many other things, will we have such kind of big scale of the data? So that's kind of the motivation in terms of like how we are going to best leverage some kind of the prior knowledge that has been learned from some kind of the pre-trained image models or the video models in terms of like using this information to produce the many other things. Because for the image generation, the video generation, for those like the diffusion models, we know that like billions of the data have been used. And these models basically can produce like very high quality of the outputs and also in the very wide the diversity. So here the question is that how can we leverage those kind of the information to produce any other things as well? So that's kind of the basic idea. So for example, like how about those kind of like 3D kind of shapes? So basically we can find those kind of 3D shape in some kind of the online the repositories for those kind of data. But obviously it'll be very hard to basically collect some kind of good quality of like such kind of 3D models in the scale of the billions, right? So if we really see some kind of a scale of the public data set, both for the 2D data and for the 3D data, then we can see that for the 2D images, as I mentioned before, we have some kind of scales of the 5 billions of the images. But if we see the scale of the 3D data, in the public 3D data, the biggest one is still kind of the 10 million. So you can see the kind of the difference of the scale, like the 5 or 6 billion is kind of like corresponding to the, like similar to the population in the world, right? Compared to that, the 10 millions is kind of similar to the population, the people in the Seoul, for example, so very small scale. So given this kind of the, well, I mean, 10 million is not very small, right? But compared to this scale, with the 10 millions of data, can we also produce like really high quality of the outputs and also in kind of the big, the range of the diversity? So here the question is that how can we still produce those kind of the 3D the models using some kind of the diffusion and the flow models? So if we consider making those kind of the images using the, like whatever, some kind of the image degenerate models these days, using the nano banana or whatever, then you can really try this, whether the image diffusion model can produce like those kind of images. And typically it works quite well, right? Because of the fact that they basically have been trained with the really internet scale of the images. So from the images in the internet scale, maybe there will not be exactly this image, but basically much more the diversity. And this kind of the diversity of the samples that we have in the distribution are basically giving us giving the model to the sense of like how those kind of images can be degenerated, right? But even with the kind of the 10 millions of the shapes, can we still also make some of these kind of the imaginable some 3D shapes? So that's kind of the questions. So what we are going to briefly discuss for today is that how can we leverage the power of the pre-trained the image diffusion model or some kind of other the diffusion and the flow models in a way that they can be also used to produce like many other things, like making this kind of some imaginable some 3D shapes, not using some kind of the direct some 3D samples, but using the 2D samples that have been used to train the diffusion and the flow models. And this kind of technique can be applied to the many other things, not only for the 3D, but also let's think about some kind of the vector images, for example, or some kind of some CAD format. Is there anyone whose major is in the industrial design or other field, or some mechanical engineering? For the people in the design field and also some CAD committee, they would want to make some kind of those kind of the 2D or the 3D data, not represented as some kind of the pixels and the points, but like more the structured way with some kind of some stroke information or the many other things. But obviously for those kind of some structured data, it's really hard to basically expect to have the data in the scale of billions. So here the question is that how can you also produce those kind of data with the very large diversity? Not exactly just like using these samples in the data domain, but based on the priors that we could learn from using that has been learned from the image and the diffusion and flow models. So this is kind of the basic question here. So what we are going to briefly discuss for today is that some kind of the techniques in terms of like leveraging some knowledge from the image diffusion models that has been trained with the internet scale the image data set to produce like many other some kind of visual of the contents. And this idea also basically can be applied to not only to generate some kind of the visual content, but for the many other things. So I didn't bring some kind of the examples here, but you can also find some examples in the internet, basically using this kind of the idea to produce some kind of the audio or some kind of the motion or some many other things. So basically the problem set up here is that we assume that we are making some kind of data that has some kind of the rendering function. I mean, here basically the meaning of the rendering is that it's basically any kind of some predefined function that is basically mapping the data that we want to generate into the form of the image. So let's say this like theta represents some kind of the visual contents. It doesn't need to be visual things, but I mean, for given the pre-trained image diffusion model, let's say we want to make some kind of the visual representation of data here, which can be mapped to some kind of the images from the specific viewpoint of the city. So let's say we have any kind of those kind of the rendering function, right? So this is something that we want to generate. And when you choose some kind of the perspective, like seeing this kind of the content, we can map the content into a form of the image using this predefined function G. So for any case that we can define those kind of rendering function, how can you basically produce the theta using the pre-trained image diffusion model? And as kind of some off topic, I'd like to briefly introduce this idea of the neural rendering. How many of you are familiar with the neural rendering? Heard about this? Yeah. And this is also quite interesting idea that has been quite popular in the area of the graphics and the vision, but you don't need to know any details for this. But here the basic idea is that we want to somehow produce those kind of some 3D output from the collection of the images from all different views. So the input is the collection of the images. And here the question is that how can you basically generate something that is representing the 3D, the kind of the object for this thing here, in a way that we can basically render those kind of reconstructed output from any arbitrary view. And this is like very classical problem in the graphics and the vision. But the interesting point in the neural rendering is that those kind of reconstruction can be done by the neural net. So that's kind of the reconstructing using the neural net basically means that actually we are having the neural network as the representation of like those kind of 3D things in a way that this can be like rendered into the form of the image. So without like having any kind of details, so this is kind of the basic kind of the setup of the neural rendering. And there are also a bunch of the techniques in terms of like achieving those kind of the goal. You can see actually quite interesting results like this. So this is like one example. This would look like a video, but actually this is not a video. This is basically generated the images in the sequence. So basically here the idea is that we are having lots of the images of this scene and doing some kind of 3D reconstruction. And as we basically play a game, we are basically navigating this kind of some virtual 3D space. So yeah, this is really just like randomly basically navigating the space in a way that we are seeing some kind of some all of the details here. And you can see that the reconstruction is not perfect here because of the lack of the information. So as you can see here, we are seeing some kind of the black sky the reason why we are seeing the black sky there is that we don't have the images there, right? So that's kind of thing. But this is kind of the examples in terms of that we are having some kind of the loss of the images with some kind of the known the viewpoint information. And based on that, we want to basically reconstruct the 3D representation of the data here. And without like, knowing some kind of the details here, especially in how we define the rendering function and how we also have some kind of representation for this, the basic idea of the reconstruction, is that basically we are performing the gradient descent with this specific gradient. So basically, we do have some kind of the representation and also the rendering function. And what we want to do is that we want to basically update the data here in a way that basically minimizing the L2 loss here. Very basic idea, right? Nothing but basically minimizing the L2 loss for all the perspectives where basically we have some kind of the given images. So this is like very high level the idea for the neural rendering. And there's also many other kind of things. Then what would be the question here? So if we have this kind of the technique that we can reconstruct some kind of 3D things, then which questions that are you going to ask? Especially if we want to apply those kind of technique for some kind of real applications. For example, like how fast the reconstruction, right? How much the computation that we will need to reconstruct this, right? And also how fast the rendering would be. Those are some kind of questions that we can ask, right? And how much kind of the big scale of some kind of 3D things that we can reconstruct based on this technique. Can you just like reconstruct a single object or some kind of a scene or like the scale of the CD or something? The scale might be also an interesting factor. And how can you deal with some kind of some moving object? If some objects are basically moving while basically taking those kind of images, then can you also handle those kind of some kind of movement of the object in the scene? Those are some kind of questions, right? Do you have any other questions? Actually, this idea has been considered for a while to apply this for some kind of the online shopping mall in a way that for some kind of products that the people are selling, we can basically put not only the images, but something like a 3D in a way that the customer basically can see the object by rotating it in the web browser, right? So these kind of things has been discussed for many applications. One of the kind of the bottleneck in terms like applying this technique for the many application is that actually we need quite many number of the images. So that's also the one question. No? I mean, how many images should we have to make some kind of the good quality of some kind of 3D here? So that's kind of some real question. And typically for those kind of 3D reconstruction, if we reconstruct a small object, and more or less like 100 images would be okay for the techniques that we can typically use using some kind of code in the internet. But let's say like if we want to basically apply those kind of techniques for the online shopping mall, then people would want to basically quickly do this kind of like 3D reconstruction. Obviously, the computation should be super fast, and also these reconstruction also should be done with some like few number of images. So when you just like take some kind of photos, like 10 photos of the object, then we should be able to still get some kind of good quality of the outputs, right? Then can you also get some kind of good 3D outputs or only from the 10 images, or the 5 images, or 3 images? So this is kind of the question. So what's the kind of the limit in terms of reducing the number of the required input images? So can you also make this kind of the technique in a way that we can produce those kind of 3D outputs only from the very few number of the images? So this was kind of the very basic motivation. And for that, one of the kind of the early idea, relatively early idea in the 2021, was that we are also leveraging some kind of the priority knowledge from some kind of the foundation model, especially this like the clip model. Does everyone know the clip model here? Everyone should know, right? So clip is like the most popular model that is basically about some kind of the relationship between the text and the image, right? So if I briefly introduce the clip for some of you who are not familiar with this, it's basically some kind of the some embedding some kind of the function in terms of that we can basically map both the image and the text into some kind of certain the embedding space. So the role of the embedding space is that now we can measure some kind of the degree of the alignment of the image and the text in this specific embedding space. So it's basically very high dimensional embedding space. And if we measure the distance over this kind of the high dimensional embedding space, after mapping both the image and the text, then we can see how close, how much they are basically aligned with each other. How much the image, this input image here, can be basically described with the given the input text. So it's basically some kind of the measure of the alignment between the image and the text. Then how can we use this kind of the information to do some kind of the few shot the reconstruction, to do some kind of reconstruction with a few images? This is like all some very practical the idea, no theory here. So here the kind of simple the idea is that, so let's see this kind of the example that we are reconstructing this like the bulldozer the image here. But let's say like we only have like 5 images or the 3 images. But the thing is that for the bulldozer image here, from whatever the perspective we see the object, this object will be bulldozer, right? Consistently bulldozer for the any perspective. So basically what we can do is that for those like the perspective that we have the images, only 3 or the 5, for those cases, we can still use the L2 loss, basically for the back propagation, basically matching the rendered image with the basically image that we have. But from the many other perspectives, basically what we can do is that we can basically simply check the alignment between the rendered image and also the text prompt that we have. Because we know that the object will be bulldozer, right? So now we basically define the gradient, not as kind of the L2 loss between the 2 images, but as kind of the gradient of the distance in the embedding space. So that's kind of very practical the idea in terms of that we are leveraging some kind of the prior knowledge of the pre-trained the clip model in a way that we can do some kind of the few shot the reconstruction. Make sense? Like just like very simple the idea. Then here the question might be is that then how much we can reduce the number of the images that that are basically required for this 3D construction using this kind of technique. So with some kind of the engineering, actually the thing is that when we start to use this kind of the clip, the priority knowledge, then we can reduce the number of the images to the 10 or the 5, even to the 3, even to the single image. It's possible that we only have the one single image, and basically for all the other perspectives, we are using the clip loss for the back propagation. But then even the extreme case is that what if we do not have any images? What if we only use the clip loss for the reconstruction? So this is kind of the first kind of the example in terms of like doing some kind of the zero-shot reconstruction. So zero-shot reconstruction sounds quite weird in terms of that we don't actually have any images. We only have the text prompt. So that's kind of thing. So without having any kind of images, what we are going to do is that here we are doing some kind of like 3D reconstruction. Now actually it becomes not the reconstruction because there's no images, but it's more about the generation, right? Only from the text prompt, what we are going to do is that we perform the same thing in terms of like reconstructing this, but now the back propagation is done with this kind of the distance in the embedding space. And the question is that would this still work? And this works in some extent, but obviously the quality is not very good. So these are basically some quality of the outputs that we could see. some very early version of the 3D generation. So now we are seeing lots of the many good quality some 3D generated models. So this quality looks really, really bad. But at the time of the 2022, I think it looks quite interesting in terms of that. We are seeing some kind of the some armchair with the shape of the avocado or some kind of pumpkin or something, Pikachu. So those are some kind of the examples in terms of doing some 3D, not the reconstruction anymore, but it's more about like 3D generation using only the text prompt. So this was kind of the first case of like seeing some kind of 3D generation using some kind of the only the 2D priors. So this was kind of the interesting example in terms of that. Now we can also produce some kind of something like this 3D, not having any kind of 3D data as some kind of a training the data that we have, but only using some kind of a 2D priors that are also learned from the pre-trained model. So this is kind of the interesting the examples for that. But here the question is that, but instead of like using the clip, can we use some kind of a pre-trained image diffusion models to basically do the kind of the same thing? So this is kind of the basic question here. And can you guess how we can basically use the pre-trained image diffusion models instead of the clip for the 3D reconstruction in this case? So as I said, while I just showed some kind of examples of the 3D reconstruction, actually you can see that this is quite the general the idea that can be applied to the many other the cases, right? So basically we want to make some kind of data that can be mapped to the other form of the data that have been used for the training some foundation model. So without really having some kind of some data samples for the format that we want to generate, using some kind of the priors of the data, some sort of the mapping from those kind of the data, and also the prior that have been learned from the some pre-trained the foundation the models, how can you produce those kind of things? So this is kind of the basic the setup. And now we want to use not the clip, but the pre-trained image diffusion model for doing this kind of thing. Any thoughts how we can do this? Denoising projection as the ground truth. What do you mean? But then do we need to perform the denoising process? So the couple of the issues with that direction might be is that, so if we try to perform the denoising process with some kind of the random, the projection from some random output would be is that we don't know whether that's, so basically the projection of some kind of the data that we want to generate should be some kind of intermediate data points that have been seen in the training of like this model, right? But would this be true? For most of the cases, it would not, right? So that's the thing. But that's kind of good try. You can really try that. That might actually, that's the kind of like worth trying, but for most of cases, it would not work because like if you try to basically map some kind of some data points into some kind of images for any kind of random outputs, then this kind of projection would not be some kind of the intermediate data points that the neural net has seen during the training. So basically, the XT that we are talking in the diffusion model should be something that is really coming from the realistic data point with the forward process, right? If the XT is not something that look like the kind of some noisy version of the clean data that we have, then the noise prediction will not work. So that's kind of the one thing. Any other thoughts? I mean, actually, there is no kind of clear answer for this. But this is really kind of the case that we want to use the generator as kind of a discriminator. So basically, for the generator, basically what we want to do is that, for example, like for the text to image generation, we want to take the text as the input and make some kind of image as the output, right? So that's basically some kind of black box kind of the things for the degenerate model. But the thing is that now what we need is basically having some kind of discriminator. Discriminator is taking both the text, image, and kind of the input, and basically checking their kind of the alignment between these two, and giving the score for that, or some kind of a distance. So the clip model can be easily used as some kind of discriminator. But here the question is how we can use the pre-trained degenerate model as kind of the discriminator as well. If we had a GAN instead of diffusion model, then it could be much easier because it already has some kind of discriminator. But for the diffusion model, we don't have the discriminator, right? So the very basic idea, some kind of practical idea, without having any kind of some good theoretical explanation, like in terms of why it works, is that the simple idea in terms of using the pre-trained diffusion model for this case is that, so if we recall the loss function of the diffusion model, the loss function was basically defined as basically matching the noise, here, right? So if we have some kind of pre-trained diffusion model, this will be the case that this loss has been converged, right? So which means that for whatever some kind of the clean the data point of the XGO, we can expect that this loss will be close to some small number, right? Something very small. So actually the basic idea is that we are directly reversing the loss function of the diffusion model. So what basically this means is that, let me go to the, yeah, so that's the thing. So if the training has converged, the loss for the realistic data point XGO will be close to the small d value. So actually, we are going to use this loss function as the measurement of the alignment. So that's kind of some very basic idea. So in the previous case, cases, if we use the alpha loss as kind of the loss function, or some kind of the clip distance as kind of loss function, now we are going to directly use the loss function of the diffusion model, while basically putting the output as some kind of the x0 the point here. So like more the procedurally, because what we are going to do is that for any kind of the given the random the data point from the perspective, we first render the 3D representation into the data point here. And then what we do is that if we recall how we train the diffusion model, we basically perform the fold process, basically adding some kind of the noise, basically making the intermediate data point of the xt here, and predict the noise using our pre-trained noise predictor, and measure some kind of difference with the noise that we added in the fold process, and basically computing the out loss and performing the backpropagation. That's kind of the basic idea. So what we can see is that we changed basically nothing, but we only changed the loss function that we are using here. So in the 3D reconstruction, we use the out loss with the given the images. For the clip-based reconstruction, we use the clip loss for the clip distance as the loss function here. And now we are using the loss function of the diffusion model directly as kind of the measure of the alignment here. So that's kind of the very practical and some kind of the some simple idea. So again, there are basically the 4 steps. We basically render the visual contents, and then basically performing the fold the process, and the predicting the noise using the noise predictor, and the backprop in a way to basically minimize kind of the altitude difference of the noise here. So here basically one thing is that since we have some kind of the differentiable the rendering function g here, the backpropagation of like this alpha loss can go all the way to the clean data point and also into the visual content here. So that's kind of key thing. So which means that our rendering function obviously should be differentiable in this case. It is clear? So this is kind of the basic idea. Like one small thing is that if we try to perform the backpropagation for the alpha difference between the predicted noise and the noise here, then using the chain rule, actually this gradient can be decomposed into these 3 parts, right? So the difference between the noise here and the Jacobian to the noise predictor with respect to the xt here, and also the xt and also with the derivative of the xt with respect to the final the visual content, the zeta here. Basically, there are the three parts, right? Which computation would be most expensive here?
To perform that task, should we pick the parameter of error predictor?
Fix the parameter of the this? Oh, yes. Oh, yeah. Obviously, this is the case that we are not basically changing the parameters of the noise predictor. Using the pre-trained diffusion model, we perform this. So the backprop, yeah, that's also kind of thing. Here, the thing is that, sorry, I think there are some kind of some notation issue. So because I'm using this data for the older places, sorry. So actually, this backpropagation should not be to the parameters of the noise predictor, but to the actually the visual content here. So I'm gonna fix the notation here. But you can also see that this becomes basically taking the derivative for the rendering function in this case, and also taking the derivative with respect for the noise predictor for all the parameters of the neural network of the noise prediction, right? So actually, this is the kind of the most expensive part in terms of the computation, in terms of performing the backpropagation. Some also without any kind of a theory, some kind of very practical. The idea is that even when you do not perform the compute the Jacobian here, basically assuming this Jacobian is kind of the one, still it basically works some extent. So that's kind of some practical the idea. So we can somehow ignore the Jacobian part here in terms of computing the gradient and also running the backpropagation. And the reason like we want to omit this is that this is the most expensive part in terms of the computation, because we need to compute the gradient for all the parameters of the neural network, right? So we want to skip this in terms of speeding up the computation. So this becomes of the final the gradient for the visual content zeta here. And based on that, we can make some kind of some 3D outputs. And actually, either we have the Jacobian parts where we do have the Jacobian or do not have the Jacobian parts. Actually, the quality is not very different. So this is some kind of the quality of the output, the 3D generation without the Jacobian parts, and also this is the output with the Jacobian part. So you can see that actually the quality is kind of similar. The only difference is that without basically skipping, while skipping the Jacobian part, we can speed up the computation, and also we can actually the computation is also kind of similar. The good thing is that we can save the memory in terms of the computation. So that's kind of the things. So now you can see why this technique is called this core distillation. So basically the thing is that we want to distill the knowledge learned by the pre-trained diffusion model in a way that we can produce like many other things, while the knowledge is basically distilled in the form of the noise of the score. So that's basically why this is called the score distillation sampling. And this idea can be applied. So actually, these are all the 3D outputs. I don't have the videos for this, but you can see that actually these are all the 3D outputs. And actually, this is quite interesting to see, right? I mean, can you imagine to have like those kind of the 3D model in the internet? Flock wearing sweater and ghost eating a hamburger. So those are really some very interesting, some imaginable, some 3D outputs, but it's really hard to expect to have some 3D models for those kind of things, right? But still we can produce like those things because we are leveraging the strong priors of the pre-trained image diffusion models that has been trained with the billions of images. And more examples with the something like many kind of weird in the outputs, right? Playing some games with some dogs here, whatever. Yeah, so many interesting outputs. So this is basically the technique that can be applied to the any data type, the type that can be basically mapped into the data space of the pre-trained diffusion model. So maybe you can think about some kind of the other the applications, not only for the pre-trained image diffusion model, but also for the molecular, for the many other things. There might be also some kind of interesting the applications for this kind of technique. So as I also briefly mentioned at the beginning, some of the applications for this is that this can be also applied to the to generate some kind of vector images. For those kind of the some stroke informations of the vector images, it's really also hard to make some kind of the billion scale of the data set. And we can use this technique to produce like those kind of things. And we are also seeing many of the some 4D examples as well. So these are also some examples that we are now using the pre-trained video diffusion model, not the image diffusion model, to produce many kind of some interesting 4D outputs as well. And also for many kind of some visual content editing, not only for the generation, given those kind of the already generate some kind of the some 3D content, if we want to make some kind of the some modification, if we just strictly use some kind of the physical priors in terms of making those kind of deformation, then we might get some kind of some artifacts like this. And by using some kind of the priors of the image diffusion model, we can also fix this kind of some artifacts and making some more realistic outputs. So this is kind of like very easy idea, and there are lots of the code in the internet. So I recommend you to try to run those kind of things and see what you can generate. And also I recommend you to try not only for the generation, but also for the editing. You can also try those kind of things. And also this idea can be applied not only for some visual content and also many other types of the data as well. But when it comes to basically, speaking to like the making some 3D using the 2D priors, what will be some kind of some failure cases if we only have the 2D information to make some 3D? So this is basically the case that we want to make some kind of some full like 3D output, while the information, the prior knowledge that we have is some kind of the partial observation, right? Not the full observation. So if we want to generate some kind of the full outputs using some partial observation, what would be some typical failure cases? Can you imagine some failure cases? Yeah. Actually, this is also kind of the case that we're gonna face for many applications, right? While we might want to make some kind of some entirety outputs, the information that we have might be some kind of some partial observations for many of the cases. So one specific, I mean, the inverse problem was also such kind of the case, but not only for like the training the model, but only for just generating some single outputs. That was also the case that we only have some kind of the partial observation. So how can we produce some like the entire outputs that can match the partial observation, right? But in terms of like producing some full outputs with the priors of some partial observation, the typical failure cases would be something like this. Let me play this. Can you see the failure here? Did you check how many faces those characters have? Obviously not one, right? Multiple the faces. So this was some kind of the very typical failure cases in terms of the rendering of those kind of 3D outputs from the specific perspective might look okay from some perspectives, but if we see the full structure, that doesn't look like some kind of realistic data point, right? Basically having some multiple faces. This is some kind of the quality of the outputs with some kind of more advanced technique, but you can still see that there are some failure cases with the two mouses here. And also, yeah, some part of the face is kind of weird, right? The occlusion is basically not correct. So this is kind of the issue in terms of like, we are making some full outputs with some partial priors. So this basically means that while we can somehow leverage the priors of the image diffusion models to produce like many other things, then we might still need to have some of the priors of the data itself for that specific domain in terms of like giving some kind of some information about some global structure of the data. So still there are some kind of limitations for that. And also one practical kind of thing is that if we want to produce some kind of the realistic outputs, then those are all the cases that we are doing still like some text condition, some kind of generation. And if we want to get some kind of the clean the outputs, then you can play with those kind of things. Typically, you need to have some very high the CFGD weight, the classified free guidance the weight. Basically, increasing this basically weight is that we are basically narrowing down into some kind of the very small scope of kind of the distribution of the data that is really perfectly aligned with some kind of a given the text prompt, which means that if you need to increase the CFGD weight, that means that you're gonna lose some kind of diversity in the outputs. So how we can also achieve some kind of the bigger diversity while maintaining the good quality using this kind of technique is also kind of some remaining kind of the questions here. Okay. Any questions on this? Okay. No question. Yeah, so this is the last topic for this class. So far we discussed the lots of topics in this class so especially for this semester, we intended to basically cover some kind of the more theoretic the background of the diffusion and the flow models the first, in a way that we are first discussing some basic idea for degenerate models and see how this idea has been evolved through the DDPM, the DDIM, and also into the continuous time deformulation, and how we can also do the SD and the ODD conversion, and how this also can be connected into the flow models as well. So those are also some kind of some foundational ideas for the diffusion and the flow models. And also for the last part of this course, we discussed some kind of the ideas in terms of like how we can also broaden the applications of the diffusion and the flow models with some kind of techniques for the inference time the guidance, and also with this core distillation. So the thing is that we haven't discussed some like many more applications for the diffusion and the flow models. And also this is also very interesting the topic, how we can also apply the idea of the diffusion models, not only for the continuous data, but also for the discrete data. So that's basically why we are going to have the guest lectures. So for the first guest lecture, the Shubham will cover some kind of the basics of the discrete diffusion, how the diffusion models also can be applied to the discrete data. And also one of the interesting applications of the diffusion and the flow models would be basically video models and also the world models. Especially the world models might be quite interesting topic in a way that many kind of some rendering the pipelines that we discussed there will not be used for many future applications. So those kind of some many future applications also will be discussed in the second guest lecture. And before we wrap up the course, here the question might be is that, so at the very beginning of like this class, I said this. Actually, there are basically two big types of some degenerate models that we are using in the foundation models these days. Basically, for the text generation, for many of the cases, we are still using the auto-realistic models. It's basically very standard thing to use the auto-realistic model for the text generation for many kind of sequential and the discrete data. And diffusion and the flow models would be the best for the many kind of the continuous data and also in some kind of the high dimensional space. But is this really true? So this is actually very interesting, the question that now we are seeing for now. Because recently, we are also seeing many kind of cases using the auto-realistic models for the image generation, and also with some kind of really good quality. So can you guess how we can also apply the auto-realistic model for the image generation? So as we know, like it's the matter of like that the auto-realistic model is basically good for the sequential the discrete data, which means that it's the matter of like how we are going to represent the images as the sequential discrete kind of things. So which means that we somehow need to discretize some elements of the images here and make some kind of like, as the sequence of those kind of some discretized the elements. So there are also lots of the ideas in terms of like applying the autonomous models into the image generation. And the kind of the good and bad things for the image generation, the autonomous model for now is that still the quality is not the best. If we only care about the quality of the outputs, for now it is still the best to use the diffusion and the flow of the models. And also for the fine tuning, for the many applications like some training free, some kind of like guided generation, we know that the diffusion and flow models might be kind of the better. The reason like why people want to still like use the autonomous model for the image generation is that we are now seeing some kind of really good quality of the language models. So here the question is that how we are going to combine like all the things in a way to make some kind of multi-model models that can produce both the text and the images. And we already are seeing some the GPT models and the Gemini models for the many things. So if we want to make some like one single model that can produce both the text and the images, what would be kind of the best way to handle that? So this is now kind of a very important question. And regarding that, still kind of the best option for now is to use the autonomous model that can basically produce both the text token and the image tokens. And we don't know exactly how the GPT models are basically designed, but many people are basically assuming that they're going to basically use the autonomous models for that, right? If we want to generate both the text and images. And also for the many open source models like this one. So let me briefly play this. So yeah, this is a open model that can take both the text and the image as the input and also produce text images as kind of the output. So really the multi-model model, right? For those kind of the models, still the best option is to use the autonomous model, not the diffusion flow models, right? So you can really check out how exactly those models are basically developed. You can check some more details there. So it sounds like then, yeah, for the cases that if we aim to make some kind of the multi-model model, then the solution still would be basically the autonomous models. Then we don't need to really, study the diffusion flow models, right? But also the interesting thing is that we are also seeing the opposite as well. I think I also briefly mentioned in the beginning of this class, but also there are many kind of some development in terms of how we are going to do the language modeling with the diffusion models. And also what people say for now is that the benefit of like using the diffusion model for the text generation is that it can be way faster like this. So you can see that like the comparison between the diffusion LLM and the autonomous LLM, and this is like only sequential generation, like one by one. All these tokens are basically generated like at each step. But if we use the diffusion model, somehow mimicking the denoising the process, then what we can do is that we can denoise like all the tokens at the same time in a way that we can produce some clear the outputs with the much fewer number of the iterations. So these are also some examples in terms of like adapting the idea of the diffusion, the denoising the process to produce some kind of some discrete data. And so which means that we are basically seeing some kind of the advances of like also applying diffusion model for the discrete data as well. And also there is the Gemini, the diffusion model, which is also another example. This is not a P. Yeah. Another example of applying the diffusion models for the language modeling. So very interesting, the situation for now is that we are seeing some more cases like applying the autoregressive model into the image and the video generation, typically known as kind of the cases that we need to use the diffusion and the flow models, right? And also there are more cases like doing some language modeling and the discrete and flow models, and we'll see how these are basically being evolved over time. And this is also one kind of the paper from the NVIDIA, which was actually released last week. So you can see some kind of the many recent advances here. Think in diffusion and talk in autoregression. So some parts of the text generation is done, especially in the beginning with the diffusion, and also the output is basically generated in a like more autoregressive way. So you can see many kind of some hybrid version in terms like combining these two. So actually, this is not just kind of the case that we are seeing some kind of the competition between these two. Actually, there's also some more the cases in terms of how we are going to combine these two. And especially when it comes to the, not only for the text and the image and the videos, if we go with some kind of the some complex types of data, for example, the graphs, like, for those kind of not the regular structure kind of the data, what would be kind of the best way to design basically make some kind of the generative model? Should we use some kind of the typical autoregressive model or the diffusion models, or can you consider some kind of the combination between these two? So there are many kind of the research going on into this direction. And also for the video generation, for many kind of cases like making the videos like this, actually videos might be interesting the example in terms of that if we see every single frame, these are basically the images, right? So we know that diffusion and the flow models might be basically the best. But actually this is the sequence of the images. So which means that actually if we consider the sequence of the images, still we might need to basically produce like all those things in like the more autoregressive way, like frame by frame. Right? So this might be also the good target in terms of like how we are going to combine the idea of the autoregressive degeneration and also the diffusion models as well. So many interesting kind of discussions going on for those kind of cases. And also for the applications, actually, we haven't discussed that much kind of the applications in this class, but actually the diffusion and the flow models can be applied to the many other things for the some molecular structure or some DNA or some kind of biological and the chemical data. They might also have some kind of some non-regular based special structures. For those kind of the cases, we can also come up with some kind of the new type of the generated models. And also diffusion and the flow models are also widely used for those types of the data, and also for the robot manipulation to basically for the robot planning for the many cases. Diffusion the flow models are also widely used, but this is also interesting in the case that we need to produce some kind of the sequence of some data points, right? So this might be also the good target to consider making some kind of hybrid version of the autoregressive and also the diffusion models. And also there are many other examples. Even the diffusion models can play chess. You can also check out many interesting examples in terms of like how the discrete diffusion can do all those kind of cases, and also solving the Sudoku as well. So this is also very recent outputs in terms of solving the Sudoku using the diffusion models. So lots of the applications and lots of some interesting types of the data. So here the question is that, so in the future, what would be kind of the ultimate degenerate model? So at the end, basically, we would gonna want to see some kind of the one big foundation model that can take all the types of data as the input, like all the text, image, and the audio, like many other things as the input, and also producing all the things as the output as well, right? For those kind of some ultimate degenerate model, what would be kind of the best way to design this? So the future might be is that actually the diffusion flow models may not be necessary. Like autoregressive, like the models might be kind of the best way to handle all the things. Or even the text would be like the next GPT might be released with the diffusion models, right? So we don't know the future. So there are many kind of questions remaining here. And I hope that this course was helpful for you in terms of like not just getting some kind of details of some theory for the diffusion and flow models, but also getting the sense of like how those kind of the techniques are basically being evolved for now. Okay, so this is the end of the class, and thank you for your participation. So as I said, sorry, let me stop this.